For our final lesson for this trig unit, this trig module, we'll be talking about inverse trig. And we'll talk about what quadrants are valid on the unit circle for you to answer questions using in an inverse manner, and what those inverse values actually are. So you'll need, again, just be able to be real comfortable with your unit circle going back and forth between the radian value and then the sine and cosine values. One big thing to remember about inverse trig is that quadrant 3 is basically a prohibited quadrant. No answer off the unit circle will ever come through quadrant 3. So you're going to find answers in quadrant 1 and quadrant 2 up until 1 pi. You'll also find answers in quadrant 4 going in a counterclockwise manner, but there won't be any answers going into quadrant 3 through quadrant 3 in any way. You have to avoid going using quadrant 3 at all. And so what an inverse trig does is it just is looking for the radian answer. So it's taking the x or y coordinate and matching it to the radian value. So this question, sine inverse, is really asking you to locate a y coordinate in one of the valid quadrants that has a y value of -1/2. Okay, a valid quadrant, a y value of -1/2. And so let's look back at the unit circle. There are two places where the y value is -1/2. Here in quadrant 4 and here again in quadrant 3. So of course, quadrant 3 is not a valid answer, so we need to use quadrant 4 as our answer. And so we have to go the shortest way possible. So we want to go to that position and we want to give the radian value that would answer that. But I can't give the name of the radian value as 11 pi sixths because 11 pi sixths is the direction that would take me in a positive way through quadrant 3 to get to that position. So I can't use that as an answer. So instead I have to use negative values to give the answer of that same position. And so I'm going to use the shorter arrow, and that shorter arrow would be a -1/6 pi. And so the answer to this trig value is -1/6 pi, which is the equivalent, we say coterminal to 11 pi sixths, but it's a shorter route and it doesn't take me through quadrant 3. If you're asked to solve, which means always get x by itself, your first step would be applying an inverse cosine on both sides. So you want to apply cosine inverse around cosine of x. And on the right side, always in front, always to the left, you'll apply the cosine inverse around -rad2/2. So what that does is it cancels out, they invert each other, so you're left with just x, equals the cos inverse of -rad2/2, which is basically asking you for the x coordinate in the position -rad2/2, and you have to give the radian pi answer that would have an x coordinate of -rad2/2. So we'll go back to our unit circle, and we're looking for x coordinates of -rad2/2. One of them is here. A second one is in quadrant. So we've got one in quadrant 2 and one in quadrant 3. We're not going to use the quadrant 3. So the shortest way to get there would be to go in a positive direction on our unit circle, and that's the position 3 pi fourths. And so the answer to this is then 3/4 of pi. Another way we use inverse trig, besides using a unit circle, is to use a triangle, because the point 4,9 is not on the unit circle, but it is on a coordinate plane. And so we draw our coordinate plane, or we sketch it. Doesn't have to be perfect. +4, -9 is going to put me in quadrant 4, which is a valid quadrant. Okay, just keep that in mind. Okay, it can't be in quadrant 3, but it could be in quadrant 1 or 2 or 4. And so this is going to create a right triangle. The right triangle must always touch the x-axis. It should never touch the y-axis. Always touching the x-axis. So there's a right angle here. Theta goes in the corner near the origin, and now I label the sides. Okay, 4, -9, +4 on that part of the triangle, -9 here, which means I need to do a little Pythagorean theorem to help me figure out the value of the hypotenuse of this right triangle. So if you'll remember, the Pythagorean theorem works on any right triangle, so a squared plus b squared equals c squared. So this is 4 quantity squared plus -9 parentheses quantity squared equals c squared. So we're looking at 16 plus 81 equals c squared, or 97 equals c squared. So this would be the square root of 97 as my hypotenuse. Now that's going to allow me to find all 6 trig values for this particular point using my right triangle. So the 6 trig values would be sine theta, cos theta, tan theta, and then matched with cosecant theta, secant theta, and cotangent theta. We'll use SOHCAHTOA for a right triangle. So the sine is always the opposite, which is -9, over the hypotenuse, which is the square root of 97. So the sine of theta is -9 over the square root of 97, which can't be simplified. The cosine is adjacent, so ca for SOHCAHTOA. And so that would be 4 over the square root of 97. And then tangent is always the opposite over the adjacent, so -9/4. So remember, that's SOH, CAH, TOA. SOHCAHTOA. Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. So using the rules for reciprocals, we can now flip each of these values to find the remaining 6 trig values. So the negative never goes in the denominator, so even when I flip it, the negative square root of 97 would be the numerator over 9, and then the square root of 97 over 4, and then the negative now would be with the 4 over the 9. So those are the 6 trig values. So what does that have to do with inverse? Well, you could be asked to find a question like this where you actually have an inverse in it. This is still going to be referencing a right triangle. Okay, it's a right triangle, cosine inverse. The values are -3 and 7, and then we have to find the tangent value that goes with it. So this is a multi-step question, but inverses also relate to the coordinate plane, or the right triangle. So we think about our coordinate plane again. We know that in cosine, the top number is the adjacent value, and the negative is going to go with the 3. So the adjacent value should be -3, and the hypotenuse is going to be the denominator. So I need to draw a triangle whose adjacent value is negative, but its hypotenuse is still +7. So that puts my right triangle into quadrant 2, like this. The adjacent value, remember the right triangle always has to touch the x-axis. So you would never draw a right triangle like this that would touch the y-axis. Okay, that would not be a valid drawing for a right triangle. It has to touch the x-axis only. And so my adjacent side is where the -3 would go. That's why it's in quadrant 2. And the 7 for the hypotenuse. And so then I'll do some a squared plus b squared equals c squared to help me evaluate this. Now a I don't know, b is -3, and c is 7. So I'm looking at a squared plus 9 equals 49. So a squared is 40. Now I don't want to put just the square root of 40 right here because that's not simplified. Now 97 in the previous example could not be simplified, but 40 can. The square root of 40 is the square root of 4 and 10. So 2 square root 10 would be the best value to list for the opposite side for this triangle. The answer to this question, or what the question is asking for, is ultimately the value of tangent. Okay, the thing on the farthest left, the most outside part, is the question. Find the tangent from a triangle that matches the inverse cosine of -3/7. So we're trying to find the value of tangent. We use the other stuff as clues. The tangent should be opposite over adjacent. And so what I have now for my opposite value is 2 rad 10. My adjacent value is -3, but I never leave the negative in the denominator, so I'm going to list my negative as part of either my numerator, or you could put it just sort of right out in front as the negative, and then the quantities 2 square root 10 over 3. We could also use our calculator to solve these problems. It's dangerous to use the inverse cosine button on your calculator because the inverse button on your calculator will only give you one answer to a problem. So it's tempting for some students to want to use, I'm going to use inverse sine here on both sides. And so x would be the inverse sine of 0.6. And this is going to tell you that you need to be in radian mode. However, if you do that on your calculator, you'll only ever get half credit because that calculator would only give you one answer. It's just a drawback of using the calculator. You'd get one answer, so you'd get half credit, but you wouldn't get all the answers on the unit circle. And so we want the unit circle here, the whole thing, in radian mode. Okay, or we can do a wave in radian mode. So it's up to you. I prefer to do a wave. So I'm going to do a graphical solution to this. So what I would do is I would graph this, and I know what sine looks like, so I'd graph sine on my calculator. I'd set my window to 0 to 2 pi. I would also graph the value 0.6, and that would be a separate entry. That would be y sub 2, and that's going to give me a line that cuts across my graph at 0.6. Then I'll use my calculator's intersecting feature to find both of the solutions. All right, so if you did just the calculator and just typed in radian mode the sine inverse of 0.6, you would get one answer. The calculator will only ever give you the very first answer, which is 0.6435. And looking at the fourth value so that I can round it to 3 decimal places, I would say 6.44, which would line up to the first answer here of 0.644. But what's the second answer? And that's only going to come by using a graph. So I always recommend checking a graph as well. Making sure that your window is set to 0 to 2 pi, and then for y from -1 to 1, because that's the amplitude. And then we'll get the second intersection point, just do a second trace, and then use the intersect feature. And then this will give you the value of 2.4980. And since that last one is a 0, we can just say 2.498. So just a word of caution, if you use your calculator and only do it this way on the calculator, you'll only get one answer and you'll get half credit. So you want to make sure that you use a graph to get 2. In the same way, we could use inverse tangent in the second example. So we could do tangent inverse. That will cancel out. I'll have x equals tangent inverse of 1. And so then if I use my graphing calculator to do the tangent inverse of 1, I will get 0.7853. So it's going to give me 0.78. But that would fail to give me the second answer. So instead, I want to graph tangent. I know that tangent goes through the origin, so it looks like this. I know it has asymptotes, which the calculator won't show me, but they're there. And there are other repeated values of tangent on either side of the first one, the period. But I also want to put on a value of 1. And that's going to give me multiple intersection points. It'll give me an intersection point to the left of the y-axis. It will give me another intersection point. That's the 0.785. And then there will be another intersection point over here before we hit another asymptote. So you just need to watch what your window is. So I look at my window over here, and that tells me to go from negative pi halves to 3 pi halves, which is basically the first 3 asymptotes. And that would be the section in between. So that would be my window on my graphing calculator. And so then I'd have a second value here that I would need to do a calculate intersection. So second trace, the intersection feature, and we get zoom in here a little bit, 3.9269. And so since we look at the 4th decimal, we want to round that to 927. Okay, so now you've got how inverse can be used correctly. So the correct use of inverse is not to use quadrant 3. The correct use of inverse is to use a graph to support your answer, because using only the inverse feature of your calculator will limit the number of answers that you get. And then using a right triangle, and also being careful that you're only using the correct quadrants for that. So that wraps up the review of trig, and we'll get together on Thursday and we'll review questions that you have, and then that will set you up for your Canvas test on Friday. All right, hope you have a good rest of your day.